I printed the seminar already, so people who want to already think about some questions. Yeah, first question, it's polynomial time to approximation algorithm for max cut. So I write something that the decision version is NP complete, and we proved it some seminars ago, at least for multi-graphs. But for normal graphs, it's also NP complete. So, but first problem, it's a bit hard. I mean, there is specific thing. Nobody online. Interesting.
But recordings are very useful.
Okay, they're useful. Yeah, because there are no lecture notes. Yeah, so you need to.
I think I see every lecture twice.
Okay. Very good. Yeah, I don't have time. Actually, we are already on the streaming now. And is it 3? Yes, it's. I should try it a little bit bigger. Let's start. So, topic of today is approximation algorithms. Somebody is online. Okay. Topic today is approximation algorithms. So we will have a definition. So, so we always spoke about decision problems, but that's not what your boss needs. He wants an algorithm that does certain things, and you need to produce something. And so sometimes it happens that decision version of a problem is NP complete, so you cannot print an exact answer, but it's enough to have an approximate answer. So if it's, for example, if you're exact within 0.1%, it might not have significant practical implications. So reason why sometimes you need exact algorithm is that in a complicated process, like 1,000 things need to be happen. If you are 1,000 times 1% off compared to competition, then your product, if it multiplies the price, then you might end up being like 10 times more expensive than competition and you lose. So that's why it is nice to have provable guarantees. But sometimes you're lucky and you are just designing some small component and being 0.1% worse compared to the competition, it just changes the price of the product 0.00001%. And so the price for research is not good to know. Okay, but it can happen that being a factor 10 off would be a problem. Okay, so now we will speak about if Buzz gives us NP complete problem, then it's interesting job and you have an excuse not to be perfect on given data set. So that's nice news. Okay, so let us say what is C approximation algorithm. For example, let's consider vertex problem. So vertex cover problem. So input is a graph and but now let's speak about a production problem. Input is graph and then question. Produce a vertex cover of minimal size. Vertex cover of minimal size. And so what is C approximation algorithm? So it receives, for this problem, it receives a graph and outputs the vertex cover such that the size of vertex cover divided by the size of optimal vertex cover is smaller than C. And we can have a parameter. And so if graph has n nodes and the input size is n, for example, then we require that our size is at most C of n. So there exists famous algorithm. Well, so given a graph, imagine that you actually need to solve vertex cover problem. So we know it's NP complete. So we cannot have an algorithm that's always fast and always produces the same answer. And so now we will relax and we don't want exact answer, we want approximate answer, and it's possible. But what might your first heuristic idea for some greedy search? So our third topic is that greedy doesn't work, but I mean theoretically doesn't work. In practice, it's amazing algorithm always works. But yeah, so no, always I shouldn't say, but it's pretty good. So there is programming exercise for informatics students from programming engineering, and so there will be vertex cover problem, and so you will see that with small tweaks, greedy algorithm. Okay, I kind of told solution already a bit, but it doesn't matter. So what might be
is good or
yeah, it's very good. Yeah, just you need to do a few extra things. Otherwise, programming exercise is too easy. So yeah, cool. So what would be greedy algorithm? So remember vertex cover problem. You get the graph. You need to generate a set of nodes that cover all the edges in the graph. So every edge should have an endpoint in this set of nodes. So what is greedy algorithm? Which point will, so we will add points one by one to the set. So which point we will add first?
which have a lot of edges connected.
Largest degree. So we take the point of largest degree, add it to the vertex cover, then remove this point from the graph and the edges around it, and then again take the edge with largest degree. So each time we scan for the largest degree. So it works pretty good. Yes. But it's not optimal algorithms. So it's not so easy to invent, but when our time does write the solution, it's okay, let's do it in different order. Let's first say why it's not an optimal solution. And so there is special connection construction. And so it can happen that this algorithm produces a solution on a graph with n nodes that is log n times bigger than the smallest vertex cover. So if n is equal to 1 billion, you can be like 30 times bigger. Well, it's natural logarithm. Actually, I forgot. Binary or not? Okay, we will see in the proof. So yeah. So works as follows. We will have bipartite graph. And on one side, so I choose parameter k. Oh, actually, sorry, this log k optimal algorithm. Yeah, log k optimal algorithm. Okay, so I choose parameter k, and on one side we have k factorial nodes. And on the other side, we will have k minus 1 groups of nodes. So here, so the nodes in the other part, they are, so here we have k factorial divided by k nodes. And every node is connected to k different nodes here. So that means that after we connect them, every node here has degree 1, and every node here has degree k. So here is the degree k. Why? Because here we have k times fewer nodes. Each node connects here to different k nodes. And then we do the same. We make a second group of k factorial, k minus 1 here. And we connect, we do the same thing. So now we have more nodes. And so here this will all have degree k minus 1. And here we connect to all different nodes from k factorial. So after we connect them, all nodes here have degree k 2. And so we continue until we end up here with the group k factorial divided by 2, actually a big group. So, and here we have degree 2, and we connect here. So that means that these nodes here, they have degree equal to the number of groups, which is k minus 1. So the degree here is k minus 1. Okay, what will greedy algorithm do? So here, the nodes have degree k, so they are selected first. So all these nodes will be selected, and then this graph, oh, I should use k over 3. So not to have, so we have k minus 2 groups.
Why we have 3k minus 1 in the second one?
Yeah, we have k degree k minus 2 here.
And now, I mean, why we have k minus 1 in the k factorial divided by k minus
1. Yeah. So here there are k minus 1 more nodes than here. And so here we make sure every node receives exactly 1 edge from here. So that's the plan.
Okay.
And then we continue, but we stop at degree k plus 3. So here all the nodes have degree k minus 2. And then we select edges here. So we apply greedy algorithm. So here we drop the degrees. Oh, yeah. No, I cannot avoid ties here. I'm sorry. So we can stop at k equals 2. Okay, so let me take those. Okay, in the beginning, it's clear all these nodes will lose degree 1. What's happening here? Oh, by the way, this is a solution in many books, but now I realize it doesn't work because if you start selecting these nodes, the degree drops. So you're not going to select all of these nodes right away. If you allow for ties, it's okay. So you start by dropping these degree by degree 1. Then you drop everything by degree 2, so you can use this and this. Then you can use this, and this.
But we
And
have
so-
k factorial divide k
Yeah,
vertices with degree k, no?
yeah.
So we can do k
Ah, no,
factorial divide
it's
k.
okay. Sorry, I'm confused.
Yes.
Yeah. Okay. Yeah. Nothing is wrong. Sorry, I'm just distracted. Yeah. So we will select all these nodes because they have degree k. And by the time we are finished, so all these nodes have degree k. And it's enough that these nodes will drop to k. So it was right. So I did everything right. Yeah. And so as long as this is non-empty, the nodes here have the largest degree k. But when this set is empty, then all the nodes here have lost 1 degree. So the degree is k minus 2 here. But these nodes have degree k minus 1. So then we will start picking these nodes. And then we continue in this way. And so we will select all the nodes from one part. While the optimal, I claim, is to select everything here. And why is it optimal? So let's look. So it's bipartite graph. And all the nodes have at least one edge. So we need to, so the optimal way is to either, so a better way is to select all these nodes. And why? So how many of these nodes are there? So k factorial on the top side. And then on the other side, we have k factorial times 1 over k plus 1 over k minus 1 plus 1/2. Yes, and so this is unbounded sum. So it is equal to ln k here. So other side is equal to k ln k. So you know about this, right? And then so we have ln minus of 1, something like this. And now we see that greedy algorithm is a factor ln k worse from the best. Well, we don't know what's the best, but for sure we know that the best is better than this. And so it must be factor ln k worse. Now, what is this in terms of the size of the graph, the number of nodes of the graph? And so we know that n is equal to number of nodes is ln k plus O1 times k factorial. So basically k factorial. So when we take logarithm, then we can use this bound. What's the name again? Stirling bound. Let's close. Can you close the door? So by Stirling bound, we have that log n is equal to k log k minus O1. And so we are ln k different. That means that so we take another logarithm. So log n is equal to k, and log n is equal to log k plus order log k. And so we see that the ratio is, so we see that greedy algorithm is not a log. So greedy is not log n over 2 optimal. It is not a log n 1/2 approximation algorithm. So that's our result. And so, our counterexample, what does it provide? A difference of ln k, basically. Or I should use ln's logarithm. Actually, Stirling bound is better to apply with logarithm. Like this. And so it is not. So ln means natural logarithm. And approximation algorithm. So that's our conclusion. But there exists nice algorithm, approximation algorithm, and it is in many algorithms courses. So instead, so algorithm is as follows for vertex cover. Here we pick single nodes. Now let's pick an edge and add both endpoints of the edge to the vertex cover. And this is two approximation algorithm. Yeah. So algorithm, new algorithm is take any edge that's in the graph, put the two endpoints in the vertex cover, and then remove these two nodes from the graph and all the incident edges, and then repeat. Well, let me draw some pictures. And so now we need to prove that this is two approximation algorithms. And the reason can be explained in one sentence. So whenever there is a matching in the graph, minimum size of vertex cover is at least the size of matching, number of edges in the matching. Why? Because what is matching? It's set of disjoint edges. So for each edge, at least one of the endpoints must be in the vertex cover. So what we did is we picked an edge at both points into the graph. So basically, generating vertex cover, our algorithm generates a matching in the graph. And it repeats until the graph has no edges. So the number of nodes we added is twice the size of the matching we found by the greedy algorithm. So that's, let me write it. So, approximate, two approx. Oh, instead of writing it, let's do an example of algorithm. On the usual graph. So algorithm, what will it do? It will first take it will select an edge and add both nodes to the matching. Then remaining graph will contain three nodes like this. So after removing blue edge, and then we select this edge, for example, and add the two nodes to the vertex cover. So the found vertex cover consists of four nodes. So this, and this node. And we know that every vertex cover of this graph has at least two nodes because we found a matching with two edges. And so we know that of these nodes in every vertex cover, at least one of them must be in the graph, at least one of them must be in the graph. So we added four nodes to the graph, but the lower bound is two. Yes.
Yes, that's the greedy.
No, that's a slightly more clever algorithm. It's two approximation algorithm. So
And we pick a random edge. Yes.
yeah, and any edge. While graph has edges, pick edge at endpoints. Vertex cover. So vertex cover is empty set. And actually remove two nodes. Plus incident edges. So that's all of the algorithm. Not yet clear for everyone, okay. And so here we pick this edge. And we remove two nodes plus endpoint. We pick this edge. So the set of picked edges is disjoint. We can never take a node twice because when we pick it, we immediately delete the node. So we end up with matching. And it means that and we need, and each time we add two nodes, we know that one of these nodes must be in the vertex cover. So our vertex cover is at most twice bigger. And so in worst case analysis, this algorithm is much better than greedy algorithm. In practice, algorithm. So what if your boss asks you, please make an approximation algorithm? What you can do now, you have many cores, it's cheap. So you run them both in parallel. And then you can say, here is data set, it works very good. And in the worst case, I'm a factor too slow. In practice, this other algorithm will never be used, but you can tell that, but you never know if there is adversary somewhere that tries. So there can be unexpected like mechanism that behave as adversary. So yeah, so what we have here is that there is double logarithm in K, so it grows really slowly, this approximation factor. Okay, so that's it for the two first things we have to do.
Done.
Well, first three even. Oh, I forgot one task. We will speak about set cover algorithm. And I will prove, I will present log n approximation algorithm. Okay, all of the lecture, we only speak about minimization algorithms, but we can also speak about maximization algorithm. Then a two approximation algorithm is an algorithm whose solution is at least half of the optimal solution when we want to make a big solution for independent set result. So independent set problem and clique problem, they are kind of very different in the world of approximation algorithms. Because for clique problem, there is two approximation algorithm. You can get it from vertex cover. But for independent set algorithm, there is no polynomial time algorithm that give constant factor approximation. So it's kind of interesting. And so now let us speak about set cover problem. So we will have ln k plus 1 approximation algorithm. So you remember from seminar, it was proven that set cover is NP complete.
But independent set is can be reduced by another problem that can be, for example, solved with approximation algorithm.
Complement of.
I mean, why independent set?
Yeah. So what we have is that the complement of independent set is vertex cover.
So
but
we can solve the vertex cover and then make a reduction.
Yeah, but then we go from solution to n minus solution. So solution is, so if we want to find a very tiny independent set, then we have to find a vertex cover that is extremely precise. You understand? Because we take n minus. So the question is, so if I give you graph of 10 to the power 10 nodes, and then you want to find independent set of size 300, like there is open question, can you find on Facebook, I think maybe in the world still most popular, can you find 300 people that are all mutual friends with each other?
But we can
Oh,
solve
this is
the,
click problem. So yeah, another one. Yeah. So can you find 300 points that are independent? And problem is that when you take the complement, you need an algorithm that gives you that solve vertex cover with precision 10 to the power 10 minus 300 to get constant factor approximation. So relative, it's very it's not precise.
but we just will have a big constant for independence. That's the problem. So we will find very big independent sets.
Yeah,
but we will.
Yeah. Okay, we can always make, if you give graph of size 10 to the power 10, you can always give 10 to the power 10 approximation algorithm. So it's not, this is not so impressive. So if you want to negotiate salary, you cannot, yeah, will not work for Okay, let's go to set cover problem. So input is a list of sets. Set one, set two, set n, and some universe U. And the question is, find minimal number of sets so that all the elements in U are covered. So question. And I, which is a subset of 1, 2, so n, so that union I and I of Si, and so that U is a subset. Okay, so here is union sign, and here is set U. So let's do that for example. So here are all elements. Well, and then let's give a few sets. So what's the minimal size of set cover here? So how many sets do we need? Well,
What is U?
all the points that are visible. That's one, that's two, that's three, that's one.
Three sets.
Yeah, three sets. So which
Second, third,
and
fourth.
fourth, yeah. So the vertical one, the three vertical one. Okay. Yes. And so now our task is LMK plus one approximation algorithm. And here the greedy works. So let us see why. So what is greedy algorithm? We take the set with biggest cardinality and then we drop all the elements. Then repeat until no elements are left.
Mhm.
Okay. And we will prove that greedy algorithm at each step decreases the number of elements by at least a factor 1 minus 1 over k. So I'm not going to write greedy algorithm because it's very similar to greedy vertex cover. So at each step, number of elements drops by factor 1 minus 1 over k. So why is it true? So why is it true on the first step? When we take the size set with largest cardinality, we must lose such a factor. So elements that we dropped is at least 1 of k fraction of number of elements we have. And so let's say U is just a set of all elements because we can drop any elements from not in U from all the sets. Well, actually, I can drop you from the problem. I can just write the union of S5, but now all I is smaller than n. Well, that's a better formulation.
We need to cover all elements, yeah.
Yeah, all the elements of the union, because if U contains, if some S contains an element not in U, we can filter it out right away. Because such elements are irrelevant. So, union. So that's another way to say. So, like all the elements in S1, they are covered by the three sets we've chosen. So it's kind of reduction. Okay, so why, if we choose biggest set, we lose at least 1k over the element. Sorry, I didn't say what is k. K is minimal size of vertex cover. So k is equal to main size of as not vertex cover, set cover. So in our example, k is 3 because we have 3 sets. If I forget to say something important, you need to tell me. Okay. Yeah.
Because we have sites, we have the same power of set, and they are all k, so we divide it by 2 times and get 0.
So there are 2 steps. So I need to prove that this ln(k+1) approximation algorithm. And so I will do it in 2 steps. I will first prove this claim and then go to this claim, ln(k+1) approximation algorithm. So the first step, why, if we choose biggest set, we lose 1 over k fraction of elements. And then you said some answer, but I had trouble interpreting what you mean, but it's more or less the correct words are there. So what is the argument? So there are k sets that cover all the elements. So he says in the worst case, the k sets are disjoint, and they all have 1 over k of the element. So in other words, there must be at least one set of 1 over k with 1 over k of the elements. Because if all the sets have strictly fewer than 1 over k elements, then we don't have enough elements in the k set to cover everything.
Why 1 over k?
Okay.
K is less than 1. How can number perfect be less than 1?
Okay, let me introduce some number m. It is equal to cardinality of so the cardinality of the union over all sets. Okay. So I claim that there is one set, so there exists an I, such that cardinality of Si is bigger at least m over k. And so what we assume, k is equal to 3. We can cover all the points with 3 sets. If this is the case, then there must be one set with at least m over k elements. Because we can cover with k sets, we can cover everything. Yeah. So if they all have smaller than m over k elements, then the sum of their sizes will be smaller than the elements that they cover, which is impossible. So the biggest, so there is one set among our special choice in the min set cover. So when we take the maximum over all the sets, we can only get more elements. And so here it is true. So when we drop the biggest set, we must lose at least 1 over k fraction of elements. But this is for the first step. For the second step, precisely the same argument works. Now we have fewer elements, but we know that even after removing some elements, we can still cover all of the remaining ones with k sets. So one of these sets must contain at least 1 over k fraction of remaining elements. And then we delete it again. So at each step, we have geometrically decreasing set of remaining elements. So now is a question, at each step, we add a new set to our set cover. And so the claim is that after S equal to ln k plus 1 steps, we have taken all of the elements. Why? So after S steps remain, how many elements remain? We start with, let's say, m elements. And then we have 1 minus, oh, and I made a mistake here, n is the input side. So, yeah, so I should say m. Yeah, so we have 1 over k to the power s remaining elements.
So we assume that we delete at least one element.
Well, that's the remaining elements.
I mean, factor is 1 minus 1 divided
Yeah,
by
yeah.
k, because the minimal size of set is 1. So we assume that we pick at least one element. Yes.
Yeah. So as long as I mean, if only one element remains, we will take it for sure. So we don't need to worry about rounding. And so there is a set with at least 1 over k elements that we remove. And so if 1 over k is times number of remaining elements is 0.0001 elements, it's okay because we promise to take at least that many elements. So we can round up. And so I can put and so we take at least, I can round up that many elements.
I mean, why we get this factor 1 minus 1 divided by.
Yeah, so it's elements we have minus elements we take.
Okay, yes.
So it's this?
Yes, it's true.
Yeah. Okay. So now I claim that if we substitute this value of S, number of remaining elements will be strictly smaller than 1. And then we are finished. So now we need to make calculation. Well, let's remove something. Example. Okay, so I will use inequality 1 over 1 minus k is smaller than exponent minus 1 over k. So it's in many areas of computer science, this inequality appears. I don't know if you will be a real programmer, you maybe never need it, but I think that, but as soon as there is a little bit of research involved, it's one of very frequent inequalities, so I should try to remember. Okay, so let us now look what is happening with our formula. So m 1 minus 1 over k to the power s is smaller than m times exponent minus 1 over k to the power s. Now the s goes in the exponent, so it's equal to m exponent minus s over k. And now yeah. So no, okay, I created a mess. So what I needed is k ln m or s. So now if I insert the correct value, things work out for us. And so we need s over k, which is ln m plus 1. So okay, we need to round up. Well, there is plus 1, so I forgot to add the rounding. So this is a symbol for rounding up. So then we have that this is smaller than m exponent minus ln of m. So exponent minus ln over n. So strictly smaller because I dropped the +1. And so this is equal to 1. So we have strictly smaller than 1. And we know that after this many steps, our algorithm is finished, has taken everything. And so here we have ln m, so m is size of universe, +1 approximation algorithm. So m is, and size of universe is bounded by size of input. So a logarithmic approximation algorithm. So let's finish this part. And now we only have two tasks left. So I need to I will give you a make span problem, a scheduling problem. So you have two cores and you have a list of independent tasks, and you want to distribute over the two cores so that you minimize the slowest finishing time of a core. So some tasks are long, some tasks are short. So the make span is the runtime of the slowest core. The problem is that tasks have different sizes, so you can like not perfectly match the runtime. And so we had some problem. I think it's called set splitting, we called it. So we get a bunch of integers and we want to partition them into two sets so that the sum is exactly equal. So this problem is NP complete. And so we cannot hope to find an algorithm that runs in time polynomial in n and give exact answer. But now we want an answer that is approximate up to factor 1 plus 1 over epsilon. So we will have a 1 plus epsilon approximation algorithm. And the runtime is 2 to the power 1 over L times polynomial in n, polynomial in the number of numbers we get. So if you need algorithm that works for epsilon 0.1, then there is the runtime 2 to the power 10 times some polynomial, and it might be doable, this algorithm. But if you need 0.1% accuracy, 1 in tau, epsilon is equal to 1 over 1,000, then no chance to run this algorithm. And so for each epsilon, we have a good approximation algorithm, but the dependency on epsilon is terrible for this algorithm. Okay.
And do we know the time that tasks will be executed? Will we have two
We
cores?
get a list of tasks with their runtimes. So we assume we know precisely the runtimes, and then we want to schedule them over the two cores. Okay, you can generalize to any number of cores, but I will just speak about two cores, then for convenience. Okay, so set splitting, I will call it. Oh, no, so how do I call it here? Make span. Question. Same one and such that maximum over some I and the sum of I and not in I, but you understand what I mean. I goes from 1 to n, and like smaller than n here of AI, like this. And so it is minimal. It's visible. Yes. So so algorithm will have two phases and two steps. So first we will take all the elements whose size is at least one epsilon fraction of the sum. Or even. Well, let's have some parameter S now. And so we will brute force over these elements. So we will consider the problem with where we only have the heavy elements that contain at least epsilon fraction of the sum's weight. We drop the other elements, solve the problem by brute force, and then we fill the two cores with the solution. And then we apply greedy algorithm, but we sort the elements downward. Actually, we don't need to sort. Just in any way, we add the elements to the slowest core. And this will give us a solution that's correct up to epsilon fraction. Okay. So let me write it. So I will call them the elements B. So consider all BI and the list A1 till AN. With BI bigger than epsilon times sum over A1 AI. So just the sum over all I. Then step 1. Solve problem for B1 till E. Then step 2 is greedy. Or to how should I call it? Let's say to the set I, each other element I, to I is sum of I smaller than sum of I. Yeah, but here the non-positive, okay.
And
Yeah.
why BI the array of A?
Yeah, so we go over the array and we pick each element, so we make a new sequence. Each time we take a element of epsilon, that's big. Actually, there is some problem with my parameters here. Those who already who already understand the proof, so they can tell me as soon as I figure out everything how to fix it. Okay, so we create a list B1, B2, and so on of all the heavy elements here. And I was okay, so I think I will get into trouble. I will need to divide epsilon over 2 here. I don't remember, so we will see it soon in the proof if there is a problem. Okay, so then we have a smaller list and we solve it on the smaller list. Maybe I should do an example of algorithm. So let's create some list, so some input. So, for example, is this readable?
Yes.
So 10, 9, 8, 8, 4, 3. Wait, I should be a bit clever. So I have 5 left. So let's so I will go for 15 so that it's easy to sum up. So then I need about 4 to 8 more. And let's say then 4 times 2. So the sum is 50 here. So here we will have 50. And let's say epsilon equal to 0.1. So then what we have to take here, all numbers that are bigger than 5. So then we have the B1 till is equal to 10, 9, 8, and 8. So then we brute force solution. So what is partition that makes them maximally equal?
Brute force, it means.
Yeah. So now,
Exponential.
yeah, exponential search. So we have to find I, a subset of elements for which the sum, for which this maximum is minimal. So we try all the subsets. And so here we have 4 elements. There are 2 to the power 4 subsets. And for each choice of I, we calculate it. So it will take time 2 to the power this size. And so 2 to the power 4 things. In general, we can have up to an element. Well, what is that's a good question. What is maximal number of elements we might need? So look to the definition. We take all the elements that contain an epsilon fraction of the total sum. So what is maximal number of elements?
I think it's n. So if
That's a bit too much.
if epsilon is very big, we will pick every element.
Yeah, so
Could be.
if this is true, we have a problem because then we need to brute force. If this is our best upper bound, we need to brute force over n elements,
Yes.
which takes time 2 to the power
Yes.
n. But this is we're dead by then.
Yeah,
So we need better
exponential,
bound. Yeah.
We assume that epsilon is have a little would
Yeah,
very
yeah,
small.
yeah,
It's
yeah.
very small.
Yeah, when we
Yeah.
do brute force, so how many B's should we take at most? So you know that. Yeah, exactly, yeah. So
How much?
1 over epsilon.
Mhm.
And we cannot have more than 1 over epsilon many elements that take epsilon fraction. It's like Markov bound. So yeah. So okay, so now we have at most 1 over epsilon elements and we brute force over these elements. So that's why we have time 2 to the power 1 over epsilon times polynomial and n. And so epsilon 0.1, we can deal with this. So we brute force over 10 elements. 0.05 still okay. 0.0333, it starts to get tricky. But we can be lucky in many cases that they're much less in practice. Okay, let's not be distracted. So we brute force here, and then we construct the cores, and we assign these elements to the 2 cores. And so they will be a little bit different. And so here my notation is not very good. And so here I mean not an I among elements assigned so far. So, or maybe I should have a set J. Let us have here the set I. And here the set J.
Sorry, and why number of elements is the 1 divided by epsilon? If we have 50 elements equal to 1 and epsilon is 1 point or 0.1, we will pick all the elements.
Sorry, I wasn't listening. I wanted to be consistent with what I write on the board here. Okay, can you repeat your
Yeah.
question?
Why we will pick 1 divided by epsilon elements? If array is array of ones and the epsilon is for example 0.1, then we will pick all of the elements.
So if we only have big elements, then we can indeed pick all of them. But then we know there are few of them, so we can brute force in any way. It can happen that there are no elements that we pick if there are no heavy elements.
I mean, we can pick all the elements on the first step. If the
Yeah,
all elements
It's possible,
is,
yeah, and then we are
one.
finished after the first step.
Yes, so it is incorrect that size of B is less than 1 divided by F.
No, we can pick all elements, but if we start with few elements, then we are okay.
So we when we have 1 divided by epsilon elements, we just stop stop picking.
Yeah, so it can happen that our algorithm is doing nothing in this step, and so we are finished by after this step. You don't need to program anything, just make sure that it's allowed, your code works correctly if this set of remaining elements is empty. Okay, so now let us understand why we have epsilon approximation algorithm. And so we have already, let's take, since you mentioned, let's take this step. Imagine that the no elements are left here. Then by construction of first step, we have exact optimal answer. So now imagine that after second step, I was still doing some illustration. So what was my question? So what is the brute force answer for these 4 elements? We have a bit fewer. Okay, so what is the minimal value of this maximum?
10 and 8.
Yeah. So in the first one, we take 10 and 8. And in the second one,
9 and
yeah, I should better do like this. 9 and 8 and 10 and 8. Yeah. So, and the difference is only 1 in our example after this step. And then we do the greedy step. So we haven't done yet these ones. So when we assign the 4, we go to the first one where we have 9 and 8. So we add 4 here. So let's make it a bit realistic here. Then 3. So at this moment, this one will be shortest, so we will add 3 here. And at this point, the cores have equal work. And then we have 4 times 2. So each core will get 2 by greedy algorithm. And so in our example, algorithm is perfect. Okay. So now let us go through the proof back. So we did already one case. If there are no elements left in step 2, we have perfect answer. Now what happens if, so there is one that is shorter. Imagine that in the greedy step, there are only, and so the difference is a bit larger, and we only add to 1 core, the smallest core. Then I claim answer is also perfect. And so we have some difference, and then we add a few small elements here, but we only use 1 core here. Then I claim that our answer is optimal. Well, especially if we add them here in sorted order, then the answer is exactly optimal. But in particular, we are at most epsilon from the optimal answer. So I claim that here, so this is the time we get, and then there might be the shortest time that we get. So our answer might not be optimal, but at least it's epsilon from optimal in this case. So here is the last one we got from brute force. And then we know that when we added this last element here, this element is smaller than epsilon. But we added to the smallest core, so we know that this core was not didn't have the biggest load. And so to the smallest load, we add epsilon. But the optimal load must be bigger than this core. So optimal load must be bigger than this score. And we added at most epsilon here, epsilon fraction of the load, but we started from some earlier point. So in this case, the difference, so the distance from optimal load to current load must be smaller than epsilon. So we are good in this case. But it means we also in the general case, we are good for almost the same reason. So what happens when we add the last element? We know that before adding the last element by greedy algorithm, so before we add the last element from greedy algorithm, we know that this point from the smallest score must be smaller than the optimal point. Why is it? You see why? And so I claim that before adding the last element, the load on the smallest core must be smaller than the optimal core. Why? Because the load is full on both cores below this line. So there is no algorithm that can schedule these things smaller than this line. So this line, and then we add the last one, which has size at most epsilon fraction of the sum. And so we have epsilon approximation algorithm. But actually we get epsilon over 2 approximation algorithm. Let me think, or at least very close to epsilon over 2 algorithm. And because it's actually enough to take here epsilon over 2. As well,
What is
yeah. No. Let's just keep. We cannot do much better. Yeah. So sorry, I'm wrong. Yeah. We cannot do much better. Okay. Additional trick is when you run greedy algorithm to sort elements downward. It will help because then you are guaranteed that the last one. So the non-optimality is the last element that we added. So by this proof, we can only gain practical, but in theory, I don't know how to express the advantage. So probably we can do something with epsilon over 2. I should think about it for some next homework question or exam and what we can exploit by it. But in seminar, there is a similar problem about how it's called bin problem. Like you have a bunch of tasks and you have to put it in. So okay, it's a very famous problem where you have basically the same, but so there is the make span, but the load is max. So there is a maximum load, and you have to put it, and you need to minimize the number of cores. So the task is you need to finish by a certain budget, but you need to use minimum number of cores.
And we on the first step, we pick only 1 divided by epsilon elements. Yes?
Yeah.
Wait.
Yeah, because here we have a sum, and then we can. So it's like Markov inequality. If you have probability, so you have some probabilities, then that you can not have too many elements that have at least 1/10 of.
But
No.
what if we have like more elements than 1 divided by epsilon?
No, it never happened. It's impossible. Okay, so so here our sum is 50.
If all elements of array A is
Yeah.
1, and
Yeah.
we have 50 elements, and the
Okay.
epsilon is 0.1.
Yeah,
So we
So
will
then
pick all of the elements of array A.
no, you say epsilon is 0.1 and then 50 elements equal to 1.
Yes.
Okay, so then the sum is 50. And so epsilon is what, 0.5 or 0.1, sorry,
0.1,
so- yeah,
So we
okay, so 50 times 0.1, it's 5, so you
Yes.
pick 0 elements.
yeah. So
Yes, so it's like probability, so you can think
Yeah.
about the AIs of probability. So you say that ith element has probability AI divided by sum of AIs.
mhm,
And then the question is how many elements have probability at least epsilon?
mhm.
But you know probability sum up to 1, like here. So we can have at most, so picking element is the joint event, we can have at most 1 over epsilon elements here.
Thank you.
Okay, next time I will explain with probabilities. Okay, we only have one little task left. So now we did this task. I just need to tell definition of p task and fp task. Okay, so p task says polynomial time approximation scheme. It means that for every epsilon, we have a polynomial time approximation algorithm with precision 1 plus epsilon. So we have polynomial time 1 plus epsilon approximation algorithm. Let me say one more time. So so problem has p task if for every epsilon we have polynomial time 1 plus epsilon approximation algorithm. So here we have for every epsilon polynomial time. So when epsilon is fixed, we have polynomial time approximation algorithm. But when you need high precision, this is, if epsilon can be really small, this is useless. Hence, we have also fp task. It means that there exists one algorithm that for each epsilon computes 1 plus epsilon approximation in time polynomial in both n and 1 over epsilon.
Mhm.
And so here we don't have polynomial time 1 over epsilon approximation algorithm. Oh, there is another example, but you already know this. How it's called again? Knapsack problem.
Mhm.
So in every algorithm course, you solve knapsack by dynamic programming. And this is fp task. Right? Because you round down all the values or round up. Yeah, there are values and weights. So you round them in some way, and then you do dynamic programming. And so the size of the table is polynomial in number of objects divided by epsilon. So this is fp task for knapsack. But know that here numbers are kind of in unary. And so when we put them in binary, we don't have fp task. By the way, so we know that clique and independent set and vertex cover do not have fp task. So can you understand? So if we believe that p different from np, we know for sure that clique and depend all this, let's say vertex cover does not have fp task. So why? So how can we? So let us say again, what is fp task? Algorithm that runs in polynomial time in 1 over epsilon and n, and it gives 1 plus epsilon approximation. Okay, imagine that we have algorithm that solves vertex cover with, and it's 1 over 2n approximation algorithm. Then this algorithm produces optimal vertex cover. Because we know that so imagine that we have, it's kind of important. So we have 1/2n approximation algorithm for vertex cover is exact algorithm. Why? We know that answer of algorithm divided by optimal size of vertex cover is smaller than 1 plus 1/2n. But we know that optimal vertex cover has size at most n, where n is number of nodes. So it means that the vertex cover produced by algorithm needs to have the optimal number of vertex, must have optimal size. And because if we multiply both sides by n, both sides by size of vertex cover, so we need that vertex cover is smaller than vertex cover star plus vertex cover star over 2n. But this here is smaller than n. So this term is bounded by 1/2. The only way that our algorithm satisfies condition is if it produces exact answer. And we know that it's impossible to have polynomial time algorithm. So we have here, so we know that if P differs from n, but just in practice, no point in trying to invent FP tasks for all these problems where the answer is bounded by polynomial in the input size. So that's why for these approximation algorithms, we will always speak about problems with numerical values, like the set splitting problem or make span problem. So in general, make span problem, you have more cores. I don't know how it is defined in the literature. I think there is for every k, there is a make span problem where you have k cores. Okay. Yes. So I think this was everything for the lecture, and we have 4 minutes left. So you can ask another question.
So this is clear if epsilon is very small, but if it is big, we will find.
Yeah, you can still be lucky that yeah. Okay,
So-
that's
so
a good point. Yeah.
What is the bound for epsilon?
Yeah. So here for vertex cover, we know that epsilon is really small. We are out of luck, but you're right. When we say, okay, we're happy with epsilon bigger than 1/log n or something. But then 1/log n is kind of special because we can still have exponential time. So here, when we say epsilon is at least 1/log n, then this algorithm also works in polynomial time. So for such epsilon, it should be easy to come up with algorithm because you can do so you will fail, I think, for independent set algorithm. So that's in 2 lectures. We will speak about, actually, I cannot remember at the moment what's happening. But for click, sorry, what I'm saying. Yeah, then the question is, what if epsilon is like 2 to the power minus square root of n or something? And then you might be right. So this is a very small epsilon in practice, incredibly small. But our result P versus NP does not prevent us to have FP tasks, but if we restrict epsilon to be bigger than this thing. Sorry, I'm saying nonsense here. No. I mean something else. And this is too big because it is small, still smaller than n, so the arguments still work. But there is some kind of middle ground. So when we have epsilon equal to 2 to the power minus square root log n or something. So it's possible that so then it's a non-trivial question. For this epsilon, can we solve vertex cover problem and polynomial time.
But if epsilon is like 10,000, it is okay.
If epsilon is 1/10,000, okay, so now you pick constant, well, then it's vertex cover solvable and time 1/10,000, approximation, I don't know the answer. If you can do something practical. Yeah. Okay, so it's exactly time now. So next lecture is parameterized complexity. So then you need to sleep well because it's very interesting lecture.